ఇక్కడ చూసినాం బిడ్డ. Yes, good evening. Today I'm going to give the overview of formal languages and automata theory. First of all, automata is nothing but mathematical representation of a language is nothing but automata. Basically, we're having four types of automatas. In that, first one is finite automata. Second one is the full-blown automata. Third one is the linear bounded automata, and fourth one is Turing machine. Okay, and language is nothing but simply you can call it is a collections of string, and the string is nothing but it is a collections of alphabets, and language is denoted with the L symbol, and whereas string is denoted with either W or S. Sorry, move over, please, sir. Right, sir. Okay, their language is nothing but it is a collections of strings, and the string is nothing but collections of alphabets or collections of symbols. Here, an alphabet is nothing but it is a finite and non-empty set of symbols, and it is denoted with sigma symbol. Okay, alphabet nothing but it is any symbol or any number, any special characters like at the rate, a symbol like that. Okay, and it is denoted with symbol sigma. Okay. And then coming to the strings. String is nothing but it is a finite collections of symbols from an alphabet. For example, if sigma equal to a comma b, then various strings that can be formed with the sigma are a b, b a, triple a, a b b. It means it is a combinations of a's and b's over an alphabet a comma b. And then language is nothing but it is collections of an appropriate strings. Then language is defined using an input set. Then input set is typically denoted by letter sigma. For example, sigma equal to epsilon 0, double zeros, 3 zeros, 4 zeros up to infinite number of zeros. Here the language L is defined as any number of zeros. Let's see the example for languages. The set of all the strings over a comma over ABC that has substring, it can be written as within the square bracket, you have to mention that is XACY or it contains X comma Y. Like that, you have to define the languages. Then finite state machine. Finite state machine, it is a type 1 machine. So actually, there are four types of machines, right? So in that, finite automata is a type 1 machine. Finite state machine is nothing but it represents the mathematical model of a system with a certain input. This model finally gives certain output. The input is proposed by the various states. These states are called as intermediate states. The finite state system is very good design tool for the programs such as text editor and lexical analyzer. It's the definition for finite automata. Each and every automata are defined by some tuples. Finite automata defined by the 5 tuples. Those are capital Q, sigma, delta, Q naught, F, where Q is nothing but set of states which is a non-empty. Here sigma is nothing but input alphabet. It indicates the input set, and Q naught is the initial state that is belongs to capital Q. F is the final state that is belongs to capital Q. And coming to the delta, delta is nothing but a transition function. This transition function defines mapping from the input state to the current state. Mapping to the state to the current, current state to the all the inputs of the given alphabet. Let's see the finite automata model. Finite automata model consists of 3 parts. Those are input tape, tape header, and finite control. Input tape, it is a linear tape having some number of cells. Each input cells contain one symbol. You have to place one symbol in each cell, and each input string is ended with a dollar symbol. And coming to the finite control, the finite control decides the next state on receiving the particular input from input table. And there are actually two types of finite automatas are there. Uh, uh, First one is the finite automata with output, and second one is the finite automata without output. Okay, coming to the finite automata with output, again there are three types. First one is the DFA. DFA can be abbreviated as deterministic finite automata. Next, second one is the NFA. NFA nothing but non-deterministic finite automata, and third one is epsilon NFA. Epsilon NFA nothing but NFA without epsilon modes. So coming to the deterministic finite automata, the finite automata is called deterministic finite automata if there is only one path for specific input from the current state to the next state. If we take, for example, sigma equal to a comma b, and I'm going to make the transition from Q naught to with A and with B. Means there is only one specific path from Q naught with A and Q naught with B. Okay, such type of automata are called deterministic finite automata. And it has 5 tuples and it is denoted with M. Why? Because it is a machine. Then a machine M equal to capital Q, sigma, delta, Q naught, F, where Q is the finite set of states which is non-empty, and sigma is the input alphabet, indicates input set, and delta is transition function or mapping function. I already explained in finite automata mapping, we are going to map the current state to the input symbols. We can determine the next state using this function. And there is a formula for to finding the mapping where delta equal to Q into sigma tends to, here Q is nothing but set of state and sigma nothing but set of input alphabet. We're going to map current state to the input symbols. It will goes to the only one state. It means there is only specific path from current state to the current input symbols. It means order is only one state to the current state to the current input symbol. Then coming to the second type of automata, finite automata, that is non-deterministic finite automata. The finite automata is called non-deterministic finite automata if there are more than one specific path from input current state to the current input. Okay, and this is also denoted with the M, and M consists of 5 tuples. Those are capital Q, sigma, delta, Q naught, F, where Q is nothing but set of states which is non-empty, and sigma is input alphabet, indicates that it indicates the input set. Delta is a transition function or mapping function. We can determine the next state using this function. And here Q naught nothing but initial state which is belongs to capital Q, and F is nothing but the final state which belongs to the capital Q. Coming to the transition function, there is a formula to find the transition function, that is Q into sigma tends to 2 to the power of Q. 2 to the power of Q nothing but there are more than one specific path from current state to the current input symbol. Whereas in DFA, single path, it means Q into sigma tends to Q. But here Q into sigma tends to 2 to the power of Q. Means more than one specific path from current state to the current input of the given alphabet. Then see the differences between DFA and NFA. DFA means deterministic finite automata. NFA means non-deterministic finite automata. For every symbol of the alphabet, there is only one state transition in DFA. That is Q into sigma tends to Q. And coming to the NFA, we do not need to specify how does the NFA react according to some symbol. And DFA cannot use empty string transition, but NFA can use empty strings transition. DFA can be understood as one machine. NFA can be understood as multiple little machines computing at the same time. DFA is more difficult to construct. NFA is easier to construct. So if you wanted to convert the finite automata within the finite automata, there is a possibility to convert NFA to DFA, but you can't convert the DFA to NFA. Why? Because NFA having more than one path. So you can easily convert that into the DFA transitions. It means in single path transitions. And this is the language hierarchy diagram. So I said that there are 4 types of automatas and there are four types of languages and 4 types of grammars are there, right? So coming to the automatas, I said 4 types. So first one is the finite automata. And push down automata, linear bounded automata, and Turing machine. Coming to the grammar, we're having again 4 types of regular grammar, context-free grammar, context-sensitive grammar, and recursive enumerable grammar. In the same way, we're having 4 types of languages are there: regular language, context-free language, context-sensitive language, and recursive language. Here, finite automata, regular language, and regular grammar are considered as type 1 automata, type 1 grammar, and type 1 language. Coming to the second type of automata is PDA is the second type of automata. It is nothing but push down automata. And context-free language, context-free grammar. These are the type 2 of type 2 automata, type 2 language, and type 2 grammar. Is it clear? And coming to the DFA architecture of DFA. So this we have input type having input type is divided into cells, right? So we're going to place one symbol in each cell, and input type is ended with the dollar symbol, and we have to use finite control to read that input type symbol, right? Yes. And there are two ways to represent the any automata. So first one is the by using transition diagram and transition table. Transition diagram means it consists of states and transitions. Coming to the transition table consists of the rows and columns. Are going to represent the row. We're going to represent the states in row wise and all the inputs in column wise. Is it clear? Let's see the example how to construct the DFA for the given language. Yes. Yes. In this diagram having two states. Those are Q0 and Q1. Q0 is the insert state and final state, and final states are represented with the double circles, and insert state is represented with the arrow marks. In this diagram, let's see the transition functions for this diagram. Q0 with 0 input, it goes to the Q1. So Q0 into 0 tends to Q1. So that is a actually sigma equal to 0 comma 1, right? Means we have to make the transition 0 comma 1 with the all the states of the given diagram. So we are having two states, right? Q0 and Q1. So to make the transition with Q0 with 0 and Q0 with 1 at the same time, Q1 with 0 and Q1 with 1. Yes. Here I can Q0 with 1 goes to Q1, that is with 0, and Q0 with 1 goes to itself only, that is Q0. So these two transitions are formed with the Q0 state. Then coming to the Q1, Q1 with 0 goes to Q0 and Q1 with 1 goes to Q1 only. So how to make the all the inputs, how to make the transitions to the current state. Then how to accept the string from the given DFA. So while accepting any string, whatever the chosen string, that in the string last symbol of that string mustn't should be reaches to the final state. Then only you can say that the given string is accepted by the given DFA. If it is not if it not reaches to the final statements, the DFA not accepted by the given string. So in that way, how to draw the transition diagram based on the conditions. Next one is the non-deterministic finite automata. This is the second type of finite automata. Non-deterministic finite automata also consists of 5 tuples. Those are capital Q, sigma, delta, Q0, and F, where Q is nothing but a finite set of states, sigma nothing but a finite input alphabet, Q0 the final, Q0 nothing but it is initial state which is belongs to the capital Q, and F is nothing but final state which is belongs to capital Q only. Coming to the transition function, here we are going to map the each and every state. Means here there is what do you say that is I mean compulsory we're not going to map with the all the inputs with the current state. Okay. But here more than one specific path from current state to the current input symbol. For that you can use the formula Q into sigma tends to 2 to the power of Q. 2 to the power of Q is the power set of Q, a set of all subset of Q. That is, we're going to represent with the transition function with the delta symbol, right? That is del of Q comma S. These are the examples of NFA, how we are going to consider the NFA for the given language and given string. And coming to the next, coming to the equivalence of DFA and NFA, how we are going to equal, maximum or minimize, or how do we're going to map with the NFA with DFA. So in the first one, you can convert, actually we're going to convert NFA to DFA. No, so can't convert the DFA to NFA. Why? Because there is a single path from current state to current input to the given language in DFA, whereas in NFA there are more than one specific path from current state to the current input state. That's why you can't convert the DFA to NFA, but you can convert NFA to the DFA. Yes. Then coming to the third type of finite automata, that is epsilon NFA. Actually, without input, you can't move from one state to the other state. But here, there is a chance to move from one state to another state by using epsilon. Epsilon symbol is used to move from one state to the other state. So it is same as NFA only, but here we can't. Here we can use epsilon as input symbol. So with the help of epsilon, you can move from one state to the another state. Okay. Then how to find the epsilon closure? Let's see the definition for epsilon closure. Epsilon closure denote the sets of all the states reachable from Q by 0 or more epsilon transition. That is the definition for epsilon closure. Yes, if you want, yes, this is the example to find the epsilon closure. In this given diagram, I wanted to find the epsilon closure of Q naught. So epsilon closure of Q naught nothing but there is a formula itself plus epsilon reachable state from the Q naught. So itself nothing but Q naught. I can reach from Q naught to Q1 with the help of epsilon, and with the help of epsilon I can reach to the Q1 to Q2. So epsilon closure of Q naught is nothing but Q naught, Q1 and Q2. And then next you have to find out the epsilon closure of Q1. Q1 nothing but itself plus epsilon reachable state. Itself nothing but Q1. I can reach from Q1 to Q2 with the help of epsilon. So epsilon closure of Q1 nothing but Q1 and Q2 only. Then we have to find out the epsilon closure of Q2. So there is no epsilon transition from Q2 means we have to consider only itself. Then epsilon closure of Q2 equal to Q2. In this way, we have to find out the epsilon closure of each state in the given diagram. ఏమైంది ఆపేయచ్చా సరే క్లోజ్ చేద్దాం ఏం చెప్పిందో